right, I just wanted to make a quick video going over some of the things we didn't get a chance to talk about today. So just to run through the answers to each of these questions. So what's so special about countable sets? Well, their elements can be enumerated, which means that when you're denoting them, you can write actually there's one way you can denote the set A as listing its elements, A1, A2, A3, dot, dot, dot. Now it is important that the dots continue here. This indicates that the set is infinite. And without that, if I just ended at some A sub n, like this is what question 3 is talking about. If I just ended there, then we would not have a countable set. You would accidentally be using a finite notation to refer to an infinite set. So the answer to 3 is no. This is a finite set. So it is super important that you get the dots in there when you're denoting a countable set. And getting at the answer here to question number 2, when you suppose that A is an uncountable set and you denote it this way, the reason this is wrong is because this is like saying the moment you denote a set using A1, A2, A3, dot, 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 you've made the assumption that it's countable. And uncountable sets are not countable. They cannot be put into one-to-one correspondence with the natural numbers. So this implicitly assumes A is countable. And sort of an important fact here is that uncountable sets cannot be enumerated. If they could be enumerated, then you would basically have a way to define an onto map between the natural numbers and that set. The fact that elements of a countable set can be enumerated, it automatically arises from the fact that there exists this F that's a bijection from the natural numbers to your set A. And F of n maps to the nth element of your set A, and that's how you enumerate it. So that's very similar to this schematic diagram I have down here. The enumeration, the reason a countable set's elements can be enumerated is because of this bijection that basically tells you which one should be listed first. That's the one that corresponds to 1. The second element is the one that corresponds to 2. Third is what corresponds to 3, etc. So you definitely cannot do this with uncountable sets, as uncountable sets have larger cardinality than the natural numbers. And you're never going to be able to find an onto map that includes every element of an uncountable set in an enumerated list. So on Zoom, we talked about the answer to A. We said here, this is just our way of trying to shake up the way we naturally want to think about the word countable. It's like, can you count the things or not? But in mathematics, it really means countably infinite. And so if you only have finitely many elements, then you're definitely not countable because you're not in one-to-one correspondence with the natural numbers. We gave the answer for B. The answer for that we said is yes. And coming down here, we have our bijection. So F is a bijection. It's clear that every element is listed in this bijection and that it's hit exactly once. So F is a bijection. I'm not going to require you all to give me rigorous proofs that the functions you define are bijections, but it should be clear from your definition that every element in the output space is getting hit exactly one time. So I said at the end what's sort of weird about this is that the natural numbers is a proper subset. So n is a proper subset of the natural numbers with e and pi thrown in there. Proper just means it's contained in but not equal to, so it's smaller. And we've just said that a set that is a proper subset of another one, actually they have the same number of elements. This shows us how things can get weird when you have infinitely many elements in play. There's a lot more space for how you pair things together. And so coming up here and thinking about question B, the integers are also a countable set. The key to being able to do this is to come up with a mechanism, sort of a pattern for how we go about labeling integers. Now we know we're trying to take the natural numbers, which is all the positive integers, and put those into one-to-one correspondence with all integers, not just the positive integers. So we need a way to sort of chunk the integers into finite chunks so that we can sort of enumerate and count over them. And a natural way to do that, looking at C, is if I'm thinking schematically, I want a labeling system for how I'm going to label each of the integers. And I need to do this in a systematic way so that it's clear that every integer appears in this list. Now, I'm not able to just enumerate all the positive integers first and then label the negatives, because I never finish labeling the positive integers. I'd never get back to labeling the negatives. So I have to shuffle them together. So the first thing I'm going to do is I'm going to take 1 and send it to 0, because 0 is sort of the odd man out. There's no, it's the only integer that where you're not seeing plus or minus itself in there, although technically 0 equals plus or minus itself. But then after that, I can just go through enumerating the integers in chunks, where I just think of a finite chunk as being plus or minus the number. So I want to make sure that I label the positive and the negative version of an integer before I count and go on to the next one. So next I would do 2, -2, 3, -3, etc. And I could have written -1 and then 1, -2, then 2. There are lots of ways that you can enumerate the elements. In no way is the bijection that you find going to be unique when you're able to put two sets into correspondence. So in this way, if I wanted to write a formula for how this works, and I want to define a bijection from the natural numbers to z, then I can think about where does each natural number go. And what I see is that there's sort of this relationship where the negatives all get defined, sort of alternating, and zeros included in there too. And then I've also got the positives that kind of map to each other. And since there's this alternating pattern going on, that tells me that my bijection is probably best defined in terms of even and odd branches. So what do I do when n is even? What do I do when n is odd? And so when n is even, if I take a look at the correspondence between the numbers, so I'm looking at all these orange highlighted pieces. When I plug in 2, I'm supposed to get 1. When I plug in 4, I'm supposed to get 2. 6, 3. And I start seeing that the number this is going to is just n over 2. For the odds, it's a little bit trickier, but what I see is that I'm actually just subtracting 1 off my n value. So I'm going to do n minus 1 divide by 2, but then that all needs to be negative. Let's check that that works. When n is 1, so when I'm 1, I'm supposed to go to 0. So when I plug in 1 here, I get 1 minus 1 is 0. So that does work. Now let's try 3, make sure I get -1. So I plug in 3, 3 minus 1 is 2, 2 over 2 is 1. Multiply by a negative, that works. I can check for 5 and 7, and I'll see that they work as well. So this is perfect. So F is a bijection. So therefore, we can say that Z is countable. Or another way of saying that is that Z has the same cardinality as N. So again, weird. It seems like there should be twice as many numbers in the integers as the natural numbers. So twice as many integers as natural numbers, since you've got all the positive ones and all the negative ones, and then you're also throwing in 0. So it's like you should have twice as many plus 1. And so we're starting to uncover sort of just how strange infinite cardinality can behave. And then to think about number 5, we're actually going to think about this a little bit differently. I'm going to go ahead and ruin the surprise, but R and the open interval from 0 to 1 are both uncountable sets. They cannot be put into one-to-one correspondence with the natural numbers. And for this one, because we're not going to be trying to write them in one-to-one correspondence with the natural numbers, we're going to move away from our schematic diagram that we were doing for number 4. And instead, we're going to think graphically. Is it possible for us to try to draw a function that maps between R and 0, 1? So thinking of this, one of these is going to be, one of R, or that interval, is going to be the domain, and the other is going to be the codomain. And it doesn't matter the direction in which you define the map. So it may be helpful for you to think of the domain as being, for example, between 0 and 1. And can you imagine a graph that hits all of R between that? That's 1 to 1 and onto. Or instead, you could think about generating a graph where the domain is all of R, and the goal is to hit every number between 0 and 1, and do so in a 1 to 1 and onto fashion. So sort of passing our horizontal line test that we came up with earlier. When you do this, you start to think, okay, let's look at this first try where we use 0, 1 as the domain. So I'm going to make a function f. It's going to go from 0, 1 to R. That's what I would like to do. If I'm going to hit every real number and I'm going to do it in such a way that I have a 1-to-1 function, then I don't want my graph to turn around, because the moment it turns around, I'm no longer 1-to-1. I don't pass the horizontal line test. But I want it to continue up and hit every real number, and also go all the way down and hit every negative number. And what I end up getting is something that looks like this. And this should remind you of something. This looks like tangent. If I had started over on this other one and I tried to do this second option where I took the reals as my domain, and let's call this function g, we'll say it goes from R to the open interval 0, 1, I need to hit every single number between 0 and 1. And so here I'm going to have to sort of have the same thing, but it looks like arctangent. Now we shouldn't find that surprising, because we said that the moment that you can prove that A has the same cardinality as B, then you can also show that B has the same cardinality as A just by using the inverse of it. So here we're seeing that under one formulation, our function looks like tangent, and on the under the other, it looks like arctangent, and those are inverses of one another. Now, it's important to point out that these graphs are not exactly the prototypical example or the standard graph of tangent or arctangent. In graph 1, it's not quite the tangent because it has a shifted domain. The domain that we're used to seeing this graph over is from negative pi over 2 to pi over 2. And similarly, when I go over to number 2, it has a shifted range with respect to the typical arctangent. Usually we see that between negative pi over 2 and pi over 2. So this gives us an idea. maybe what we can do is instead we could show that 0, 1 has the same cardinality as the open interval negative pi over 2 to pi over 2, and then show that that has the same cardinality as r. We know that we're going to have a one-to-one function that maps from negative pi over 2 to r, simply because that's just the tangent function. So what we would like to do is define some other function, h here. And the question is, we want a bijection h from 0, 1. So we're basically just doing a translation of an open interval to another open interval. And then overall, then we will have a bijection, I'm going to call it f, from 0, 1 to r, defined by, well, first, if you're going to plug in an x from the open interval 0, 1, you're going to say, here's my x. First thing I'm going to do is map it over under h. I'm going to map it to the interval negative pi over 2 to pi over 2, and then I'm going to follow the tangent function over to r. So that says finding f of x is going to first take x to the interval negative pi over 2 to pi over 2, and then it's going to plug it into the tangent function. So what we've used here is transitivity. And what's left to be shown is how exactly do you create a one-to-one correspondence between the interval 0, 1 and negative pi over 2 to pi over 2. Well, again, graphically, I know that I'm only supposed to be graphing over the range. I don't need to map 0 anywhere, and I don't have to map 1 anywhere, but I do need to map the open interval between them somewhere. The easiest way to do that is to create a strictly increasing function, and it actually looks, like this, for example. You can just use a straight line between them. This passes the horizontal line test. If I draw a horizontal line at any value in the codomain negative pi over 2 to pi over 2, it's going to hit the graph exactly one time. So h of x ends up being the linear function between the point 0, negative pi over 2 and 1 pi over 2. So you can compute that line. I'm not going to compute it. But ultimately, you're just going to say, hand me the interval 0, 1. I'm going to first put it into this linear function to transform it to the appropriate domain, and then I'm going to take that domain and plug it into the tangent, and then I'm going to have all of r, and in that way, I'll be able to say that 0, 1 has to have the same cardinality as r. So that's the trick.